Strictly speaking, it is rather easy to define a class of functions on metric measure spaces and call them Sobolev functions. But the deeper question is whether they do deserve the name Sobolev functions, whether they exhibit any of the behaviors of Sobolev functions that we know of in the Euclidean setting. For example, your Sobolev function is not just any measurable function, but actually it has a representative that cannot be changed arbitrarily on higher code, even smaller codimension subsets. And for example, if you are in W1P, the functions are actually more integrable than you expected. And other, for example, absolute continuity along many lines property of Sobolev functions. So the question is, once we do define a class of Sobolev functions, will we have any interesting object? And the answer is, in general, no. On certain metric measure spaces, certain definitions of Sobolev functions will only give us the class of LP functions, just integrability and nothing more. So they really will not have any particular behavior that distinguishes them from measurable functions. The one property that really makes the theory of Sobolev functions on metric measure spaces much richer is the requirement or the assumption that the space supports some form of Poincare inequality. And when you do know that your space supports such an inequality, the class of Sobolev functions becomes much richer, and the functions in that class do exhibit some nicer behavior than your arbitrary measurable functions. Also, for the fear of making stupid mistakes, I'm going to go ahead and assume that my measure is doubling, because that is often coupled condition together with the Poincare inequality. So this would mean that there exists some constant C, at least one by necessity, such that measure of a ball with twice as big radius as B is controlled by C times measure of the ball. We mentioned this briefly before, so that we don't want to pick up extreme amount of volume in just going equal distance away. So this is B. It has a center and a radius R. So 2B will be the set of those y's with distance to x less than 2r. So our balls will be open balls. It's not always the case. In some papers you would see that the default definition for a ball is closed, but we go ahead with open conditions, open balls. So what is meant by a Poincare inequality? Well, many different things are meant with a Poincare inequality. At this point, we do not have even one definition of Sobolev functions, so we necessarily have to go with Lipschitz functions. So recall that a function from x into r is Lipschitz, or more specifically a Lipschitz, if for every x and for every y from your space, the difference of ux and uy is bounded by L times the distance of x to y. We have seen that by Rademacher theorem, for example, that Lipschitz functions are quite nice. They have a derivative. So if your space is actually a piece of Euclidean space, for simplicity I'm assume all of it, if you have a Lipschitz function on a Euclidean domain, then U is differentiable almost everywhere, at Lebesgue almost every point of your domain. Also, Lipschitz functions are in the classical Sobolev space, and Okay, on a general metric space, you cannot talk about differentiability, but then there is a notion that kind of captures the rate of change of the function, and that is the local Lipschitz function. To illustrate the point, so you could have a function that goes from x into r. The Lipschitz constant L is a global quantity, so if you have values of u that are about 0 on this end and about 1 on this end, and this diameter is something like 10, then the Lipschitz constant will be comparable to 1 over 10. But what if your function actually is much more constant, say intermediate here? For example, your function has a rise from 0 to values 1 on this part, and then from that part on it's pretty much constant for the rest of the space. So you don't want to say that your derivative is comparable to L, to 1 over 10 on this range. You rather want to say that the derivative, whatever it is, of u here is 0. And therefore, this global Lipschitz constant L does not really capture that behavior. The replacement is this definition of local Lipschitz constant. So given u from x into r Lipschitz, we define at every given x from your space the local Lipschitz constant of u at x to be, okay, you compare values of ux and uy to dxy, and then you localize. And because you don't know if this limit exists, so you have to take lim sup as y approaches x, which means y is not equal to x, so that this fraction has a is well defined. Yes, and then from there you know that this quantity is defining you a finite value. Finite because we know that each fraction is less than L, even if x is and y are not close to each other. We know this is always less than L, so the lim sup will also be less than L. So if I go back to my previous example, in this blue region, you definitely will get this local Lipschitz constant of equal to 0. So this is kind of the roughest notion of a derivative of the function u, here only for Lipschitz case, that we have available at this point. And this is enough to let us define what we mean by a Poincare inequality on a metric measure space. So of course it's inspired by the fact that in the Euclidean space we do have this inequality as a theorem, but here we cannot act in an axiomatic way. It's a definition, and then we inquire whether a space does support a Poincare inequality or not. So we say this metric measure space xd mu supports, sometimes we may say it has, or it admits, many synonyms, but the whole idea is that we say it satisfies a p Poincare inequality for some p bigger than or equal to 1 if there exists constant c and constant lambda bigger than or equal to 1 such that okay, so measure of balls is positive and finite for every ball in X, and so this is just a technicality required so that I can define the average value over the ball of some function. And in this case, I will have u minus average value of u on b. So I take this average value of u on b once to get this number ub, and then I subtract u, I do u minus ub, which is just another non-negative function, real valued function. I take absolute value, and again I integrate this over the ball and divide by measure of ball to get the average. So all integrations are respect to d mu. Don't worry, I will write down the definition of average just to make sure it's clear. So this is like how much on average is u different from the average value on the ball, and we require that this be controlled basically by the size of the derivative. In this case, it's just the Lipschitz constant of u. So this, and being a p Poincare means that the p integral of familiar power 1 over p from LP. So this is basically LP norm of the Lipschitz constant, local Lipschitz constant. And even in the Euclidean case, this will not be true without this diameter of the ball multiplied here and the constant c. What is u then? So we require that this inequality holds for all balls in X and all Lipschitz functions u on X. Okay, so that is just the definition of what we mean by a p Poincare inequality. Okay, so sorry, this lambda does not appear. So this is lambda times b. So you are helping this side by enlarging the ball by lambda, because lambda is bigger than or equal to 1. Okay, so the key notion again here is that the average oscillations of function are bounded by the integral of the gradient. So we will talk about every single detail of such inequalities. This will be our business for the rest of this discussion on metric measure spaces. So diameter here appearing, we will see why it's significant, why multiplying by this lambda is significant and important, and when we can actually when we can afford to take lambda equal to 1 so that we don't have to enlarge this, and many more. So even this definition of Poincare inequality is not universal. So sometimes if you begin by a different notion of differentiability, for example upper gradients, and you define your Sobolev functions before talking about Poincare inequalities, then you can use upper gradients to define what you mean by Poincare inequalities. And also the question whether that definition of Poincare inequality gives this definition and vice versa are always quite interesting questions. And the nice thing is that in nice spaces, under not too restrictive assumptions, you do obtain the equivalence that, okay, if you have Poincare working for all Lipschitz functions, you actually have it for all Sobolev functions. Okay, so I promised that I will write down this definition of average in case it's not a familiar notation for you. So given a set E under X with measure of E positive and a measurable function of course mu measurable, so from E to R we define the average value over E of the function G, the mu just to be integral of G over E and then divided by measure of E. That's why we require this measure to be positive, and also why we require that the balls have positive measure. Infinity also is something we probably wouldn't want to see. It probably makes everything trivial. Okay, hopefully now everything makes sense. Okay, in follow-up videos, I will try to give basic, say, subsets of Euclidean spaces type of examples of metric measure spaces, and then ask whether they have Poincare inequality plus the other type of properties that we discussed, like about being geodesic, being quasi-convex, whether the measure is Borel, doubling, and things like that. At this point, what I would like to mention is that having Poincare inequality and also having a doubling measure together have immense consequences on a space. So maybe we can talk about them in detail later on, maybe once we know a little bit of results. But the heuristic is that having a Poincare inequality implies that the space is very well connected. That there are many rectifiable curves between any given 2 points. And for example, the simplest fact is that if you support the Poincare inequality, your space has to be a connected space. This we can just easily prove if you have two separate connected components of your space X, then you can put a constant value in here. So you can say, let's say U is just 1 on this set, and then you can have U equal to 2 on the other set. This is a Lipschitz function, and local Lipschitz constant is 0, so if you plug that into this inequality, you will see that you get 0 on this side and something non-zero on that side if you take a ball large enough so that it picks a value from both of these balls. So if you take such a ball and apply the Poincare, it will fail. So you see that from that inequality, you get something topological about the space and that it is connected. But this is like the simplest observation to begin with. What happens is that the smaller the P is, the more connected your space is. So we will see later that we always aim for the lowest exponent P for which we have Poincare inequality. So we will see that if you have, say, two triangles as subsets of R2, and then they are just joined through one vertex point, you can, it inherits this metric from R2, say, and the measure is just L2 measure restricted to this thing. Because of this curves collapsing, so basically all the rectifiable curves that go between these two parts have to all boil down and go through this bottleneck. And exactly because of that, it turns out that there is no Poincare inequality for p less than or equal to 2, although we do have p Poincare if p is strictly bigger than 2. So also the critical value of the p is also very important. Okay, so many of the stuff that one wishes to do on metric measure spaces become possible if the